I'll be with you in a moment. All right, thanks, Bob. Appreciate the introduction, and I'd like to thank the Geophysical Institute for organizing the lecture series and Raven Landing for hosting this event, and thanks to all of you for showing up. It's the reason that I'm here as well. I'll tell you a little bit about myself before I get started. As Bob mentioned, I study carbonate rocks for the most part, which are limestones, and that's sort of my specialty, is studying sedimentary rocks that are deposited in the ocean. And most limestones are made up of a lot of fossils. They're made up of marine organisms, and you can tell a lot about what the ocean was like by looking at those marine organisms, usually under the microscope, and trying to understand what kinds of things were there and how they changed through time. And so that's some of the stuff that we'll be doing, that I'll be doing with the cores that I'm working on here for the Chicxulub event. I first got involved working on Chicxulub back in about 2001 when we had an impact crater specialist was working at UAF, and he walked into my office one day and he asked, and there was a new core that was being drilled back then, a different core than the one I'll be talking about tonight, and he asked if I wanted to work on the limestones that were deposited on top of the Chicxulub impact crater, and I said, of course. I couldn't turn an opportunity like that down. It's a tremendous project. It's one of the most exciting things that I've worked on in my career, and so I'm happy to share some of this really interesting research with you tonight. And so the title of the talk mentions that this impact sort of heralds the dawn of a new era. And so I'm going to try not to use a whole lot of geologic and scientific jargon tonight, but I will need to introduce a few terms that are geologic. And a lot of you may know that the geologic time scale is divided up into eras. And we have the Paleozoic, the Mesozoic, and the Cenozoic eras. Paleozoic means ancient life, Mesozoic means middle life, and Cenozoic means recent life. And this impact event occurred at 65.5 million years ago at the boundary between the Mesozoic and the Cenozoic eras. And so it really does literally mark the dawn of a new era. And so that's hence the title of the talk. This project has evolved over the years. There are a number of different cores that have been drilled into the Chicxulub crater. Some of them were drilled by oil companies way back when they were doing exploration work back in the 70s and 80s. And then there was this other core that I just mentioned that was drilled back in 2001, which is an academic core. And then this core that was drilled by an organization called the International Ocean Discovery Program. It's IODP for short, and this organization has been drilling in the oceans for several decades, going back into the mid-80s or so, and they usually use various drill ships for their research and research drilling. The one on this side, the Geoides Resolution, had a little bit of a refit back in 2007, 2008, but it's been running basically since 1985. And there's a newer ship that was built by the Japanese. It's largely been working in Japanese water called the Chikyu since 2007. But the area where this core was drilled on the Yucatan Peninsula is basically just too shallow to take these large research vessels into. And so they just couldn't take them. We had to take this thing in, which is called a lift boat. And as you can see, it has these three big pylons on it. Those pylons are the feet that are going to be basically lowered down to the seafloor, and then this thing is going to be jacked up on those pylons. And we're here off the coast of the Yucatan Peninsula, just northwest of the town of Progreso. The water here is about 30 feet deep. So it's just too shallow to get one of these big research boats in. And so they brought this jack-up barge, this lift boat called Myrtle in, and started to do some of the drilling on it. And so I'll talk a little bit about some of that process as well. The Gulf of Mexico back in 65 million years ago or so was a little bit different looking than today, but not a whole lot. You can see that we have this nice big shallow shelf area off the Yucatan Peninsula. That's still kind of there, but it's a bit deeper at that point. We haven't had as much limestone deposited in that area at that point, and so a lot of the limestone that's there has been deposited since this impact event. And so there's a little bit deeper water here when the impact occurred. On average, it was probably about 600 meters deep, but it deepened from something like 100 meters very close to the shoreline to maybe 2 kilometers, 2,000 meters as you get deeper into the ocean basin. And so that actually changed a lot about what we think about how this impact affected things, because there was a lot more water involved than we initially thought, because we thought it was much shallower initially, and so this gives us a little bit more insight. So this lift boat Myrtle, as you can see now, it's in place. It's jacked itself up onto these 3 big pylons, which are settled onto the seafloor, and so it's very stable. It's about 30 feet above the sea surface, and so you've got this big crane here. That's used for all kinds of things. When boats come in to bring supplies, the crane lifts the supplies up onto the boat, but it's also basically used as an elevator. They have this little platform that they lower down off the edge of the lift boat and bring on personnel that are going to be working on the boat and on the coring project. And so this is basically a portable drill rig. It's moved out. It's a good bit smaller than the research vessels, which they normally use, which have a whole suite of labs in them. And so you could only have about 10 scientists go out onto this platform when normally they would have about 30 scientists. So it's a very small scientific crew. These are some of the roughnecks, the guys that are doing the actual drilling. They've got a little placard here. It says 1,000 meters below the seafloor. That was the day that they hit that depth. So you can see them at work here. This is the actual drill bit that they use, and you can see it has a fairly wide hole. That's where the core is going to be taken. And so this drill bit gets lowered down into the water, and eventually to the sea floor. It's rotating and it's cutting into the rock, and so there'll be a core tube inside of here that will collect the core as it's drilled down into. And so this little diagram kind of shows the drilling process. So you've got this drill pipe, or sometimes called a drill stem, and so they're continually adding on new pipe at the top. It's going down to the sea floor, drilling in. They will put in a casing at least part of the way down. There'll be drilling mud that's pumped down into there, and that's basically a mud that's got a certain density, so it will keep this thing from collapsing from the weight of all of the pressure that's underneath the surface of the earth. You basically have pressure coming from all directions onto that drill stem, and so you need to pump this really high density mud in there to keep all of this sort of in place. And that mud gets pumped in, and then all the little bits of rock that get broken off get pumped out onto the seafloor, and then the core is basically just taken up through that tube. It's about a 4-inch core. These are the chief scientists of the expedition. This is Joe Morgan from Imperial College London, and this is Sean Gulick from the University of Texas Austin Geophysical Institute. You can see that they've got some of these cores here, and they're in this plastic tube. Because we have this very, very small lift boat out here, we couldn't do any of the research on these cores that they normally do on the ship. And so what they did was they put them in these plastic tubes almost immediately. They might have scraped off a little bit of material at the top and the bottom of the core just to try to get some information about what might be there. But basically it went into these tubes and it went into a freezer, and then it got shipped to Germany, which I'll tell you about in a little while, the whole process of analyzing this core. This is just a photo of the IODP science crew as well as the IODP staff that were on board, and so about 20 or so people that are working both in the science and staffing the whole operation out there, other than the drillers. And so I'll talk a little bit now about Chicxulub and impacts, and I'll just throw up this outline as I go along just to keep myself in line. Impact craters, as I said when I started, I'm a sedimentary geologist. I knew very little about impact craters when I started on this project. I've had to learn a lot. It's a fascinating topic, and it's basically a fundamental process in the solar system. We have impact craters on every planet that can sustain a crater in the crust. You have sort of a continuum of impact craters from very, very simple ones like this one called Victoria on Mars. And the simple craters are basically a fairly bowl-shaped structure. They usually have a bit of an upturned rim around the edge, and you can kind of see that in the photo you can see the shadow from where the rim is upturned on this portion of the crater. So that's a very simple, small crater. There may be on the order of hundreds of meters across, maybe a couple of kilometers, tens of kilometers. But then when we get up to these very large craters, things that are on the order of hundreds of kilometers across in some cases, we get very complex craters with multi-ring basins. You get a series of rings that form around the interior of the crater. Sometimes the crater will have just a simple central uplift. Sometimes it'll have this ring of mountains around the center of the crater. Sometimes that ring of mountains will be really continuous, like this one. Other times it might be fairly discontinuous with little breaks here and there in the actual ring of mountains. And these really are mountains. They're thousands of meters high in some cases. This is actually similar to what we see at Chicxulub. It's not a nice complete circle. It does actually have some breaks in it. And so just to give you a little perspective on how big this impactor was, here's Fairbanks. Everybody knows sort of the size of Fairbanks. That's the size of the impactor compared to Fairbanks. It would obliterate this whole area. If we looked at the size of the Chicxulub impact crater here in central Alaska, it would stretch from Nenana almost all the way to Central. So this is a big structure. Did a lot of damage to the Earth. And so let's talk a little bit about how these things form and what goes on when something like one of these big rocks literally hits the Earth. Something really amazing happened 65.5 million years ago. When you have an impact, it causes an area of the Earth's crust to literally break up. We call it deformation. It's deforming because of the energy of the impact. And so it literally causes this stuff to act like a fluid. It breaks up the rock into such tiny pieces that it can literally flow like a fluid. And so as this material is, basically some of the material in here is going to be vaporized, literally turned into a vapor and thrown up into the atmosphere. Some of it's going to be thrown up into as small pieces, actually small to large pieces of Earth's crust being thrown up in what's called ejecta, the material that's ejected out of the crater. And then as all that material is basically removed from the Earth's crust, you have material that's basically going to well up and form a central uplift in the center of the crater. And it's totally analogous to this process. Just a drop of water falling into a puddle, and that little droplet that sort of rises up above the surface after that happens. It's the exact same process. It's just going on literally with the Earth's crust. So that's a pretty amazing thing. As this central uplift goes up, it's basically going to start to gravitationally collapse on itself. At the same time, the walls of the crater are going to be collapsing inward, and this whole thing is eventually going to form this fairly flat crater, which may have this peak ring, or it may just have a central uplift, just with a little peak in the center. But in the case of Chicxulub, we think we have this kind of peak ring around the center of the crater after the impact event. And so this is a model, a computer model that was put together by Gareth Collins, another one of our colleagues who's from England. Very complex computer code that I don't understand, but it's a model that tries to show what happens when one of these impacts occurs. And just to kind of go through the parameters of the model, we're looking at a 14-kilometer diameter impactor, so that's the asteroid that's coming in. It's traveling at about 12 kilometers per second, and I've given you some conversions here, about a 9-mile diameter impactor, about 27,000 miles per hour. And the model here is looking at trying to show what the crust of the Yucatan Peninsula looked like at the time. The calcite in here is meant to indicate the limestones that were sitting on top of the crust. The granite is sort of what we often call the basement of the rocks here. And then dunite is another mineral that's, we think, very common in the Earth's mantle, so the stuff that's under the crust. And so this impactor is going to come in, it's going to hit, and what I'll do is I'll run through the model once, and then I'll come back and run through it again, because it goes fairly quick. And I'll run through it again, and I will just point out some of the major features here. Okay, so we've had this impact come in. It's excavated a crater, and the scale on here is in kilometers. I know a lot of you may not be familiar with metric system, but a kilometer's a little more than a half mile or so. And so we've excavated a crater that's almost 20 kilometers beneath the Earth's surface. It's sending, this is referred to as the ejecta curtain. So that's the ejecta, the stuff being ejected out of the crater. It's going up over 40 kilometers above the Earth's surface. So what I want you to watch now is what's going on right here in the center. So that's the central uplift. it's risen about 30 kilometers above the Earth's surface. That's a long way. You're taking literally granite crust of the Earth, and you are creating a fountain that's 30 kilometers or so above the Earth's surface. And I'll run it one more time and just point out the last bit. So what I want you to pay attention to now is what's happening here, and we'll come back and we'll talk about this in a little more detail later. But you can see that this granitic material is literally flopping over on itself, and it's covering up the limestone or the calcite that was at the very top. And so this is literally coming up and flopping back over on itself, and that's what we think is creating the peak ring of these massive craters. And so this looks very flat now, but the peak ring would be a slight topographic peak, literally on either side of this crater. And so if we were to look at sort of a hypothetical cross-section through this crater, this is the same line here, A prime, and so we're going right through the center of the crater. This is where the drill core was taken, this newest drill core, and so it's basically here right on the peak ring. And so you've got a series of rings around this crater, which are essentially following these down-dropped faults. These are literally faults that are cutting through the crust of the Earth that have been created by the impact itself. And so each one of these faults on either side would have a ring that encircles it. And so you can trace those rings around. And then the innermost of those rings is going to be the peak ring. So how do we know about that kind of crustal structure? How do we figure out what's underneath the surface of the Earth that way? There's a number of different ways we can do that. We can use various kinds of geophysical data. And this map here has a couple of different things on it. The base map that we're looking at, you can see the Yucatan coastline shown in white. And you've got all these colors here. What those colors mean is different amounts of gravitational attraction of the rocks that are underneath the surface. And you get different kinds of rocks in different places. Some rocks will be more dense than others, and they'll have a greater pool of gravity than something that's less dense. And so the reds indicate things that are very dense and high gravity. The blues indicate things that are very less dense and very low gravity. And what this blue feature right here is the peak ring. And so the reason it's not very dense is because that material has been so fractured up that it's very porous now. It's very different than any granite you would have, say, in your countertop or something like that. And I'll show you some pictures of it later. And so that gravity data tells us something about the character of those rocks in the subsurface. The other information on here, these lines that you're seeing, are what are referred to as seismic survey lines. And they're showing you where a ship has traveled over the water. So this is all offshore, where ships have traveled over the water and taken readings of the subsurface using this technique called seismic stratigraphy, basically. And I'll show you how that works here in a second. But so back in 2005, they did these red lines, and then these black ones were from 2006. Rather from 1996, so an earlier experiment that looked at this area as well. And so what you do to collect this seismic data is you have a ship that's sailing across the ocean. It's carrying a streamer behind it. It has a bunch of things stretched out behind it that are called hydrophones. They're basically just a microphone. And what you're going to do is take this thing, which is an air gun, and you're going to blast it into the water, and it's going to send sound waves down into through the water, and it's going to hit the surface of the seafloor and then penetrate the seafloor, and it's going to bounce back up and tell us various things about the thickness and some characteristics of these rocks that are in the subsurface. And these air horns are basically just like those canned air blasters that people use at sporting events and stuff. It's exactly the same thing. It's just a much bigger one and makes a much louder noise. And so the results of this kind of seismic work gives us something like this, a cross-section that lets us look into the subsurface and see some of the features. And what we can see here is interpretation that's laid on top of this data, but you've got various features in here, like this very sort of reddish area in here. It has some places where you can see there's offsets along it. Those are the offsets along these faults that were created by the impact event. So you can see that we have a very bowl-shaped structure. These faults are literally bowl-shaped. They're rings that go all the way around the feature. And other things that you can see the rim of the crater here, and then everything that's above this purple line is basically the sediments that are infilling the crater that were deposited after the impact event, and that's actually what I'm most interested in. The purple line is tracing the top of the peak ring, and so you can see it has a bit of a topographic high there. It's a little bit lower on this side, and so that tells us that it wasn't one of these continuous peak rings. It had maybe it was broken up a little bit here and there. And so this crater structure is fairly well defined by these large-scale faults that are showing these down drop into the center of the crater, and basically have a fairly flat crater floor otherwise, other than the peak ring. Okay, so let's just talk a little bit now about what the effects were of this impact, and then we'll come back and look at some of our results and things a little bit later. I think all of you are aware that this impact event spelled the demise of these guys. Dinosaurs, I think everybody loves dinosaurs. They're definitely the most charismatic megafauna that we've ever had on Earth. All the dinosaurs didn't die out, though. There were some that survived. And so what we had, well, I'll just introduce the whole idea of mass extinctions. There are several other mass extinctions in the geologic record. There are 5 over the past 500 million years or so. This is the one that we're talking about here. About 75% of all species on Earth died out about 65.5 million years ago. And so we had this 14-kilometer diameter asteroid impacting at that time on the Yucatan. A lot of things died: dinosaurs, various other marine reptiles, pterosaurs, various other marine things. We had various microfossils, and I'll talk more about these things in a couple of minutes. But there were things that survived. There were things like small mammals tended to survive. These things, dinosaurs. They're basically the descendants of dinosaurs. So there were avian types of dinosaurs that survived this event. And then evolution went on. Humans evolved. So we've got the age of mammals now. This is a photo of the whole group in Bremen, Germany, that was doing research on the core. And so there are survivors. We knew about some of these survivors even long before some of this research was done, the avian dinosaurs and birds. Things like burrowing mammals tended to survive better than other mammals because they were underground when the impact happened. They were shielded. We have various other kinds of things that we found by studying the core. One of the things that we see is these little tiny plates that are made by a type of algae called a coccolithophore. And these things are what we refer to as disaster forms. They come in when things are really bad, and they proliferate. They're able to take advantage of all the other things that have died out and left a lot of ecological space open, and they come in and they just go crazy. And so these disaster forms sort of are one of the first things that we see after the impact event. I also mentioned we do see some burrows, probably made by little worm-like organisms, and I'll come back to this a little bit later in the talk as well. These things are burrowing in sediment that was deposited not very long after the impact event. So life came back into this crater fairly soon after the event. So there's a lot of evidence for extinction. I'm not going to read this whole list. You can look at it yourself. I'll go through each one of these in a little bit of detail. So there's various evidence of this catastrophe that happened. And one of the first places that this evidence came from was an outcrop in Gubbio, Italy, and these deep water limestones cross the boundary between the Mesozoic and the Cenozoic. And this guy, Walter Alvarez, was a young geologist working out here at the time. He wasn't really interested in the extinction at all. He probably knew about it, but he didn't really think about the fact that this boundary was so important. He was doing some studies in here, and he noticed that there was this really weird little red clay layer here, and I'll show you that in a little more detail in a few seconds. And he wanted to try to figure out how long it took for that clay layer to be deposited compared to the limestones that are above and below it. And he was trying to figure out a way that he could do that. And he was talking to his dad one day. His dad, Luis Alvarez, was a Nobel Prize-winning physicist. And his dad said, well, why don't you look at some rare element, something that's not very common in the Earth's crust that might be coming from outer space, that might be sort of space dust that's just falling in over long periods of time. And Walter said, yeah, that would be great if we did that clay layer. If there was very little of this space dust in there, it might mean that that clay layer was deposited really, really fast. If there was a little bit of this space dust in there, maybe it would have it'd be a little bit higher than what we find in the limestones. And we'll come back and we'll look at that in a second, because this is a key piece of evidence for this impact event. The other evidence came from the mass extinction itself. That was the first thing that people saw when they were studying these rocks. One of the things that they noticed was that these marine microfossils, they're called Foraminifera or forams. They're little amoeba-like things that have a calcareous shell. This is the rock that's underneath the extinction horizon. These things are large, they're big, they're very ornamented, there's a whole lot of different kinds. And the scale down here, they're not big compared to us, but this thing's maybe a 0.5 millimeter across. Not very big, but big compared to what we see after the extinction event. After the event, they're all tiny. These photos are at the same scale. They're all tiny, and there are hardly any. There's only like 2 or 3 kinds. And so we've killed off a lot of them, and the ones that survived were really tiny. So they were really kind of stressed out. Another thing I should point out, this outcrop here is the exact same outcrop that you're looking at here. This is the boundary. It has been mined out by geologists to the point where you can't even get a sample there anymore, because people have gone in there and taken every last bit of that rock that they can get. And so we have this extinction that affects these microorganisms as well as all kinds of other organisms. But the thing that Alvarez wanted to look for was space dust. He decided to look for an element called iridium. And iridium is an element that's in the platinum group, so it's in the same group as platinum and palladium and things like that. It turns out that platinum and palladium and some of those other things they're a little more common, and there's also analytical problems with trying to analyze for them. You get interference between them, and so it's harder to analyze for them. Iridium, it turns out, is a little bit easier to analyze for. And so Luis Alvarez, Walter's dad, said, well, why don't you try iridium? That would be a really good element to look for. And so what they expected was, they might see almost no iridium in that clay layer, or they might see a little bit. They saw a lot. And a lot is 8 or 9 parts per billion. It's not a very big number, but they were expecting numbers in the parts per trillion range. So the minute Walter saw this, he knew something was off. He knew something weird had happened here. He wasn't sure that it was an impact, but it got him reading a lot, got him thinking a lot about it, and eventually that seemed to be the only explanation, was that this iridium had to have come from an impact event. We do have iridium on Earth, just not as much as you would find in, say, an asteroid. And so just the amount that they were finding here seemed a little bit strange. About the same time, there was another geologist working in Spain at the same boundary, found some iridium. There's another scientist working in New Zealand, found some iridium. Another scientist working down here in Arizona, found some iridium. By the time we've collected all of this data, we have iridium anomalies at this boundary all over the world. So we know that this is a global phenomenon that you can trace everywhere around the world. Another thing that we get from impact events that can't be formed really anywhere else are shocked minerals. And you're literally taking a mineral and you're whacking it with this asteroid, and you're creating a bunch of fractures that run through it. They're called planar deformation features. There's that word deformation again. You're literally breaking them up and causing them, and these white lines are a little bit hard to see, but they're tracing the directions of these planar features. You got 3 different ones in there. If you have more than 2, you can only form that through an impact event. You can form 2 in a volcanic explosion, but you can only form 3 or more through an impact event because of the high pressures that you need. And if you go around the world and look for shocked minerals at the boundary, they're all over. Everywhere that we've looked, we find those shocked minerals. Another thing that comes out of impacts is part of the ejecta, that material that's ejected from the crater. You get literally glassy-like particles. So you've melted this material, it's gone up into the atmosphere, and it starts to come back down, and it cools off so fast that it doesn't crystallize. It turns into a glass. So like the glass in the window back there, it's not crystalline. It has a sort of an amorphous structure. And that glass, it just means that it cooled off so fast that it didn't have time to actually crystallize into minerals. When we find these at the boundary, usually they're altered. And that's because these things are highly susceptible to alteration by seawater or anything else if they're exposed on the surface. And so they often get altered to some other sort of mineral. So that's usually what we would see at the boundary is these altered spherules. And if we look around the world, this same map that I just showed you a minute ago also includes all of the spherules that have been found. So they're also globally distributed all over the world. And so those impact deposits, they're going to vary as you go from place to place. If you're very close to the impact event here in the Gulf of Mexico region, you might have a really big, thick package with a lot of coarse-grained debris that's the result of that impact, all that material that's been broken up and thrown around by various processes. But as you move further and further away, these things the deposits get thinner and thinner, and eventually once you're in a really distal location like Spain, you're going to get a very, very thin deposit, maybe on the order of just a couple inches thick. And this is one from the Pacific Ocean. You can see all of this green material here. Those are the spherules. So that's all little tiny spherules that are making up this layer of basically material that was ejected from the impact crater. Then at the very top, what you find is what we often call the fireball layer. This is the dust and ash that's sort of the last of the ejecta that's settling out, and that's where the iridium would be as well. And you can see that the iridium is always at the top of these things because it's in that fine, really, really fine-grained ejecta that's coming out of the impact. Other things that happened, the impact event, when it hit the Earth, basically you created a crater not only in the Earth's surface but also in the water. The water all went away for at least some amount of time. You can't hold back the ocean forever, though. That ocean is going to rush back into that crater fairly quickly, and then it's going to start basically moving all of that stuff around that was in there that was part of the impact deposits. And so we think that the initial tsunami that came out of this impact, once the water rushed back in, it's essentially going to cause a water spout, and then it's going to go back out. And so that movement back out of the crater caused a tsunami that had on the order of 100-meter high, about 300 feet high tsunami waves crashing on the border of Mexico here. And so what this map is showing you is areas that have either tsunami deposits or slump deposits from the earthquakes that occurred from the event. And so we have estimates of earthquake magnitudes on the order of 10, which is larger than anything any of us have ever experienced, even here in Alaska. So enormous earthquakes, and then you're going to get those earthquakes causing places like along the edges of these continental margins to literally collapse in some places. And so you get slumps, tsunami deposits, and all these things telling us some other catastrophic things are resulting from this event. Another catastrophic effect is the heat pulse and wildfires that were caused by the returning ejecta. This stuff is coming back into the atmosphere, and it's hot. It's literally hot enough to cause woody material to start to burn. And so we have records of wildfires in a number of places around the world. It's still a little bit up in the air whether it was truly global wildfires. We definitely know that there were local ones around the Mexico area, but this record from New Zealand says that there were some that were far-flung that were caused by this returning ejecta. So we have a lot of soot in this record from New Zealand in the same layer where we have the iridium anomaly. And so there were definitely fires as far away as New Zealand from this event. Another major series of events that happened after the impact have to do with things going on in the atmosphere. And what's going on in the atmosphere actually has a lot to do with what was underneath the ground in the Yucatan Peninsula. And so this is a depiction of a core that was taken in the Yucatan Peninsula. The red stuff indicates the impact deposits, so we're not worried about those right now. We're worried about this stuff underneath the impact deposits. The blue is limestones and marl. Marl is basically just a dirty limestone with a lot of clay in it. Limestone and marl, there's a lot of calcium carbonate in there, which means there's a lot of potential CO2 that can be evolved off of that if you have an impact event. This one, though, is the more important one. This is anhydrite and dolostone. Dolostone is really similar to limestone. It just has a little more magnesium. The anhydrite is sulfur-rich. Anhydrite is basically a sulfate mineral. And so when the impact vaporized these sulfur-rich rocks, all of that sulfur went up into the atmosphere. And so you ended up with the returning ejecta causing heating in the atmosphere, causing possible wildfires. And then you had all of this finer grained ejecta eventually encircling the Earth, finally settling out, but you had dust in the atmosphere, you had soot, you had sulfur dioxides, which then in the atmosphere combines with water to create sulfuric acid. You also have nitrogen oxides that are created in the atmosphere just from the nitrogen that's in the atmosphere. That's going to combine with water to create nitric acid. So you've got sulfuric and nitric acid rain coming out of the atmosphere after this extinction event, or after this impact event. And so that is creating what we sometimes refer to as an impact winter. There was some period of time, we don't know exactly how long, but from weeks to maybe a few years, the sun was blotted out by the dust, and we had a cooling event due to all of these gases in the atmosphere that are impacting the way the atmosphere works. And then after all of that stuff settles out, we come out of that impact winter, you still have a lot of water and a lot of CO2 in the atmosphere from all of this limestone and dolostone that's been impacted. That then causes greenhouse warming. So you have heating, cooling, and then warming. This is all happening, within a couple of years after this major catastrophic event. Okay, so let's talk a little bit about this new drill core that was taken out here on the lift boat Myrtle. Because they were on the Myrtle, they didn't have all of the labs and things that they have here on something like the JOIDES Resolution, which literally it's a floating laboratory. It has just about anything you would want to do geologically to one of these cores. And so because we had the lift boat Myrtle, we could only have 10 scientists out there. And IODP has a number of places where they store their cores, and eventually that core will be stored at this one called the Gulf Coast Core Repository down in Texas. It's in College Station, Texas, where Texas A&M is. And because that one has all of the core that's from this portion of the Pacific as well as the Caribbean. But this repository here in Bremen, Germany is a brand new repository, and it was built to be able to do all of the lab work that they do normally on the ships. Because they have a number of these projects going on where they're not able to use one of the ships, so they need to be able to do all of this work. And so they shipped the core from the Yucatan over to Bremen, Germany, where we did our analyses on it. And so just a few shots of Bremen here. It's a beautiful small city in northern Germany, a port city, lots of scenic viewpoints, lots of art, very quaint city, very, very cool place. I'd recommend going there if you get a chance. This is inside the core repository, and they make these banners up to, this was actually hanging on the lift boat Myrtle when it was out at sea, and then they bring them back to the core repository. This place has thousands and thousands and thousands of feet of core. They have all the core from basically the Atlantic Ocean here in Bremen. And so we were working on the cores from this Chicxulub crater, and what did we do when we were in Bremen? We basically did everything they would have done on the ship, because we didn't have all the lab space on the lift boat Myrtle. And so we were describing and sampling the core. The reason that I was involved with the project was because I am a specialist in limestones, and so I was going to be the one that sort of helped organize. Oops. Come back. It was going to be the one that helped organize the visual core description for the sedimentary rocks. I don't know what's going on here. Sorry about that. And so the core analysis here includes a lot of things. We went through and we just described what we saw in the core, long detailed descriptions of what's there. But then we also collected samples and analyzed for things like the types of fossils that are in there that tell us about time. And we refer to that as biostratigraphy. We had people that were measuring the geochemical elements of the rocks in the core, people looking at the magnetism of the core, people looking at various other physical properties like the color and the density. And so one of the great things about IODP is that when they drill one of these cores, they collect all of this data on every core that they drill. And so every project has this baseline of data that anybody can go back and access. This is all public information. Anybody can go out and get these reports and start working on this if you had interest in getting into looking at core anywhere. So one of the first things that they do when they get the core is they cut it open. This is a pretty important process because these cores, obviously, they cost a lot of money to acquire. They're lots of effort goes into this process. They take one half of this core and they set it aside as an archive that never gets touched again. People might look at it, but they can't sample it, they can't take anything out of it. The other half is the working half of the core, and that's what we took, and we started cutting it up and started making samples. And so what that core looks like, this is just an example, a piece of the sedimentary portion of the core. You can see various, this is a worm burrow going through the sediment here, some other burrows cutting through various places. And so this is largely limestone, and this is what we would call marl, kind of a dirty limestone. And that's just to give you an idea of what these cores look like. And over in Bremen, not only are the scientists there doing science, but they're actually doing the work. They're cutting the samples, they're analyzing for biostratigraphy, looking down the microscope at various fossils that they're finding in the rocks to try to get an idea of how old the rocks are, looking at the core itself and describing all the various features that we see in there. And so these are the scientists at work here looking at the core, just to prove to you that I was there here in Bremen. But what you can see behind us here is this series of screens with a bunch of kind of colorful images on it, and we refer to that as the core wall. It's just 3 high-resolution monitors, and it's got these various images on here. And one of the images is just a photograph, but the other 3 images are CT scans. Some of you may be familiar with CT scans from medical work or something, and people have used CT to look at various features in core before, but this is the first time anybody has ever taken an entire core from top to bottom and CT scanned the entire thing. It's generated a data set that's about 7 terabytes. I don't know what they're going to do with it because I'm not enough of a computer person to really work with that, but it's an amazing data set, and it lets us see some things that you wouldn't normally be able to see. And so when we have this core wall up, we have all 4 of these images on it that we can look at while we're analyzing the core. And so down here we've just got a photographic image, and that's what we call a line scan photo, and there's a contraption for taking that. And then these are CT scans, and so this is the raw CT scan, so a black and white image, and then you can pull out other kinds of data from that. And so this one here, the CTA, is basically looking at the chemical elements or the atomic number of the elements that are in there. So if it's really red, it's really high atomic numbers. If it's really blue or yellow, it's going to be lower atomic numbers. And this CTD is basically kind of reading the density of the rocks, and so reds are high density, blues are going to be low density. And so right there, just looking at that imagery, you can get some information about these rocks just from seeing this core wall. Okay, so let's talk a little bit about the coring process and where we got the core. So we already talked about the location here offshore of the Yucatan Peninsula. This is one of these seismic images showing you the layers of rock and sediment that are beneath the surface. And so here's where the drill core comes in. This is the peak ring. And you can also see that beneath this surface, there's a little bit of topography in there. That's an actual valley on top of the peak ring. And they placed the drill core there specifically so that they would have an area that might be protected and might give us a better record of what's in there. I was amazed when I found out that they had done this, because it's a it's a kind of a bold thing to do, to aim for something like that, but it was also a brilliant move, because we got an amazing record of what happened after this impact event. So just to summarize what we see in the core, this is just a depiction of the entire core. And we recovered core from about 500 meters down to about 1,300 meters down. The first 500 meters they didn't core. There's a couple reasons for that. One, it saves money. And 2, a lot of the shallow limestones in this area actually had episodes where they were partially dissolved and there were caves that formed. And that really complicates things when you're drilling. If you run into a big hole in the ground, you can literally, the drill stem can drop down and it can break the bit and things like that. And so they really want to avoid trying to core within that portion that might have big holes in it. So just going from the top down, so we have these sediments that were deposited after the impact event, and I'll talk a little bit more about those. Then you have a whole big package of stuff that we refer to as breccia, which just means it's broken up rock. It's material that's been shattered and rolled around, and there's about 130 meters of that, so a pretty big thick package of breccia. And then you come down into a package that's mainly mainly granite, although it has a little bit of melt rock up at the top. This little thin sort of yellowish layer in here is melt rock. And so that's material that was literally molten. And so after the impact event, you've got a crater that's on the order of 200 kilometers across, and it had literally a lava lake in it until the ocean rushed back in. That might have only been on the order of several minutes, but for those several minutes, you had a 180 kilometer lava lake just sitting there. And then the stuff below here is granite. That's what's making up the peak ring. We're drilling directly into the peak ring, so all of this stuff is sitting on top of the peak ring. This is the actual crust of the peak ring. And I'll talk a little bit more about the characteristics of that crust because it's kind of important. We'll come back to that in a few minutes. We do have evidence of impact from the core. So this photo that I showed you earlier of these fractures, these deformation features in these shocked minerals, that was from one of the samples from the core. There's another feature called a shatter cone that only can form from impact events. And we actually found shatter cones in the core itself. A lot of times if you're looking at one of these impact craters in outcrop, you'll see these shatter cones in various places around the actual crater. We were pretty lucky to actually find one of these things in the core itself. So I want to just go through a little bit about the rocks that we cored through, and I'll start at the top and come down because that's the way we got the information. I wasn't down there coring. I was actually sitting at home with a broken ankle. I had broken it just a few days before they started drilling. So I was pretty much incapacitated, but I was getting daily reports emailed to me about what they were drilling through. And so they're drilling down through these sedimentary rocks, and they're going through this marl, this really dirty limestone, and then maybe into some clean limestones, going back and forth, different kinds of rocks. And then they went down a little further, and I'll come back to this thing I've labeled the transitional unit here. Here's the last of the limestones as they're drilling down. And then they started hitting this stuff. And the drilling reports came back saying that this was sand. Now we're out here off the Yucatan Peninsula. All the sediments out here are limestone. There should be no source of sand anywhere. And so for several days, I was getting these reports saying, sand, sand. I'm just trying to figure out where could this sand be coming from. It turns out the sand is the impact breccia. It's just the very top of it is very fine grained. And so as you go down through the impact breccia, it gets coarser and coarser and coarser. And so we're seeing the ripped up rocks that have been rolled around by the tsunamis that came through here and created this huge deposit from the impact. And so you go down further, you get some mixtures of breccia with maybe a little bit of melt rock. Here you've got melt rock, and here you've got a clast, a little chunk of the granite. It's been a little bit altered by the heat of the melt rock. Here you've got more melt rock, and you can see you've got some that's black, some that's green, and here you've got this sort of mixture of green and black. Those are actually two different rocks that melted. The green was a carbonate rock or a limestone that melted, and the black was probably some of the granite that melted. And so these two different melts are mixing together within this pool of molten rock. And then finally, once you drill down into the actual basement or the granite, it looks like this. It looks like it could be a countertop. But if you look at the properties of this granite, it's a lot different than what would be in your countertop. Your countertop is going to be a very dense granite that's going to have very little pore space in it. It's going to be almost completely solid. This granite has very low density, and it has about 10 to 12% pore space, whereas a normal granite might have 1 or 2% pore space. So that's the effect of shocking this with this impact event. So it really alters this granite, and that's why the entire peak ring had that blue color on the gravity map, because it was very low gravity because of the amount of fracturing that it was subjected to. Okay, so let's talk a little bit about impact craters and peak rings and how they form. So we've already kind of looked at this model a little bit. It's referred to as the dynamic collapse model because it's talking about the dynamic collapse of this central uplift and the eventual sort of rolling over of it to create this peak ring that goes all the way around the inside of the crater. There are a couple of other models for how these things form, but this was sort of the best contender for what causes these things. And I'm going to show you another little animation here, and this is a similar model, but it's just going to be looking at one half of the crater to really concentrate on the peak ring. And I'll run through this a couple times as well. This one runs a little bit slower, but you can see some of these processes going on that we're talking about. And so that right there is the peak ring that's forming as this whole thing is coming to a close. So let's go back to the beginning, and I'll just point out a few things in here. And so what you're seeing here, this is the start of the central uplift going up into the atmosphere, basically. And here you can just start to see the rollover where the limestone, so this is the same kind of layout of the model, limestone, granite, and then the Earth's mantle down here. You can see that the granite is starting to flop over onto the limestone. This is the ejecta curtain that's being driven away from the interior of the impact event. So you can see the central uplift now going up over 20 kilometers into the atmosphere. And there you can see the flop over that's creating the peak ring. And so right there is the peak ring that's basically now overlying the limestone that's folded up underneath it. And so those little explosions that you were seeing, they think those are real things that are happening. So you're releasing volatiles. You might have a lot of melt in there that can break out and burst out as like a little explosion, basically. And so they think that those are actually real things that are happening. Okay, so let's talk a little bit about some of the other, oh, I lost my core picture. Oh well, there was a picture of the core here. And I'll tell you what you're looking at, and I'll show you some pieces of it in a second here. Basically, the top of the core was in the limestone. The middle was sort of the last part of the material that's settling out after the impact, and that's what this is referring to. It's gradually settling out as all of the energy from the tsunami and various things are starting to die out. And then we actually have a tsunami deposit at the very bottom of that. So let me go on, and I'll try to point those out here. And so these are the last limestones, or the first limestones to be deposited after the impact. This is this unit that I'm talking about. It's sort of a transitional unit. It's mostly looks something like this, very, very laminated with little layers that were deposited by fairly high energy processes. But you go down below that, and this, you can see there's some bedding in here. It's angled a little bit. We think that this is a tsunami deposit. We think that's actually the last of the main tsunami deposits, and then these are really, really little things going back and forth. And so tsunami deposit, and then the first limestones up here. And in that tsunami deposit, we did some geochemistry and looked at various elements in here that might have something to do with the impactor. And things like chromium and nickel are very common in things like asteroids. They're also common in the core of the Earth. And asteroids, we think, are just a broken up portion of a planet in between Mars and Jupiter there in the asteroid belt. And so the core of those things would also have a lot of chromium and nickel. And we're finding a bunch of chromium and nickel shown in these colored patches. The chromium's the purple, and the nickel is the red. And that's basically right in here in the very bottom of this transitional unit that we're looking at. That's sort of the end of the deposits from the impact. You also find a little bit of chromium at the very top of this package, and we think that that's the result of just that fine fallout of ejecta at the very end of everything. And then the other thing that we see has to do with the return of life to this crater. And so this is the very top of this brownish unit that we're looking at, and there are these nice oval burrows here. These are made by some sort of worm that's been crawling through this sediment, and you can see that it's filled with this lighter colored material from up here. So the worm crawled through this, went down into the darker material, and that lighter material filtered down in. So that's proof that these things were living in this sediment and crawling around in it. And then up above, as we get up into these limestones, we have a lot more burrows as well, but that's fairly long after the impact event. This entire unit, we really don't know exactly how long it took to be deposited. It could have been days, could have been weeks, possibly years, but doesn't seem like it was going to be any more than years. So whether it's years or days, within years, we definitely had things that were living here, and maybe even within a few days. it's hard to estimate, but anyway, we're still working on trying to come up with a better estimate for the timing of that. We have a number of other things that we documented within this portion of the core, and so this is the very end of the impact-related deposits. We have some of these Foraminifera, these marine fossils that come from before the impact event. But they're reworked. They're just washed around. A lot of times they're broken up into little pieces. And so those things are from before the impact. Then we have these things that we refer to as disaster taxa. I showed you one picture of some of these things before. These are these plates made by these microscopic algae. And this one's referred to as Barudosphaera, and this one's called Thracosphaera. These are both things that come in when stuff just isn't going very well, and they're taking advantage of the fact that everything else is gone. We have those burrows that I just mentioned in the last slide, and then we have the earliest of the Cenozoic Foraminifera that are coming in right at the top of that unit. And so the return of life came to this crater certainly within years of the impact event, and maybe a lot sooner. And I'm just going to end with that. We've documented a number of different things within this crater. We've shown some of the processes that are going on with the deposition of these crazy breccias and melt rocks and all of the sediments that are on top of this impact crater. And it's definitely been one of the most exciting projects I've had the privilege of being involved with. And I thank you for your attention. And I'm certainly happy to entertain questions.
Thank you, Mike.